Hello, and welcome to the XNA 3D Toolkit video series. My name is Dustin Heffron, and I, along with Mr. Larry Louisiana, will help give you a set of tools to quickly get you started in a world of 3D game programming with XNA. We will be covering a wide range of topics to help you become familiar with many aspects of the XNA framework. We'll start off by covering some of the lesser known but important background information, and work our way through by building up a set of tools necessary to make a visually immersive game scene. As we progress, we'll make our code more robust and easier to change. This allows us to quickly add assets and see them work inside of our game. In Section 1, we will go over some background information about XNA, including graphics profiles, XNA-specific concepts, the graphics pipeline, and then we'll start to build some helper code to use later. But first, graphics profiles. XNA allows us to use two different graphics profiles, Reach and High Def. These profiles essentially restrict the use of certain features to simplify multi-platform development. The biggest difference between Reach and High Def profiles is the platforms or devices that they're meant to run on. The Reach profile seeks to reach or be applicable to as many Microsoft platforms as possible. This includes the Xbox 360, Windows Phone, and PC. This optimized version of the XNA framework is meant to be lightweight so that the platforms with fewer physical resources, such as a Windows Phone, can run games optimally. High Def differs in that it features a full XNA framework and is meant to be run on systems with a lot of resources, such as the Xbox and a gaming computer. Here we have some highlighted differences between the two platforms. To see more detailed information, you can always visit the official MSDN website at the link provided. One important thing to note is the version of .NET that is used with each profile. With Reach, you are limited to the .NET Client framework. But don't worry, this is just a streamlined version of the .NET framework that removes unnecessary functionality. But with High Def, you're given the full .NET 4.0 framework to use as you wish. Now let's see how to appropriately set up a project for each of these profiles. First, simply open Visual Studio. From there, go to File, New, Project, and look for the XNA 4.0 Xbox project. Type in a name for it and click OK. When it's finished loading, you can right-click on the name of the solution in the Solution Explorer and go to Properties. Or you can go to Project Properties. Here we can see the two different profiles. Currently it should be set to High Def, but we can switch it to Reach if we like. If you notice, the Xbox is restricted to the Client.NET framework. And that's about it. Now we know more about the two different deployment profiles for XNA and how to switch between them. Now that we know a little more about XNA, we need to take a closer look at some of the factors that will affect how well your game runs. The first thing to keep in mind about XNA is that it is a managed wrapper of DirectX. What this means is that Microsoft has simplified a lot of the steps necessary for you to dive into development. The advantages of this is that you don't have to implement tedious code to do things like create and load graphical contexts, implement signal processing for controller input, or decode audio formats. XNA takes care of most of this to enable you to get your game up and running as quickly and easily as possible. And if you like more advanced functionality, worry not, XNA allows you to control that as well, which we'll see in a later video. But there are also consequences to the ease of use that XNA gives you. Because it is written on top of DirectX, XNA is naturally slower. This is due to its generalized nature, allowing many different kinds of games to be implemented with ease, without specific optimizations. That being said, XNA will only run as fast as your code allows it. If you write fantastic code, your game will run well. But if you write bad code, it will underperform. But fear not, the framework is still very powerful and we're here to help you write great code. Now there are a few things that you need to keep in mind when working with the framework. The first is the game state. While we will be managing our own side of the game state, there's another game state that is managed in the background. There are functions that we can use to interact with and change this state to our benefit. But we need to be very cautious, since changing the internal state is an expensive operation that can drastically slow down our game. To avoid this, we only change state when necessary. We might do this at the beginning of the game to set up the scene, or even during the game to change the art style. In the end, we only want to do it sparingly and all at the same time. The framework also makes some assumptions about our game that we will have to work with. One of the most important is the axis orientation. XNA uses a right-handed coordinate system. What this means is that the positive z-axis, or third dimension, points out of the screen. This means that if we want to move an object forward into the screen, we must translate it by a negative value, whereas we can move towards the player with a positive z-value. We'll see how this affects our game more in later videos. For more information, please see the official MSDN documentation at the link provided. Now that we know more of the underlying concepts, we can take a look at some more advanced topics.
Once you've exported your 3D content from your favorite 3D modeling tool, you're going to need to get it into XNA. XNA provides a method for doing this called the content pipeline. In Visual Studio, what that looks like, one of these two projects here. Typically, when you start a game, it will create for you a content project for you to put your content in. However, with a lot of 3D content, you're going to need to create a pipeline extension to help you import that. However, most of those pipelines are going to be specific enough to exactly what you're importing that they don't necessarily apply to a toolkit. They have to be all custom made. If you look at the pipeline's capabilities, and this is an image that's available online, you can import FBX or .x models right off the bat. However, there are times when you need to be able to create other models, and XNA allows you to do that by giving you the ability to create custom content importers, which if your model type was a .foo, you could create a custom model importer, and then it will follow the same content importing types as an FBX or .x file. If you do that, keep in mind that one of the great places to store additional information is in the model tag. In order to add a pipeline to your game, you simply go to your solution and add a new project. When you do this, the MS Build engine at compile time will take your files and convert them into XNB files, which the .NET framework and XNA automatically recognize. Due to the one-off nature of content pipeline extensions, they do not lend themselves very well to toolkit items. Therefore, this is as in-depth as we are going to look at pipelines. Know, however, that there are plenty of ways to bring in content and extract information from them at compile time to build out whatever your custom content or your custom needs may require. What we're going to do is we're going to create a Windows game library, and this is going to be the core of our working toolkit. And in it, we're going to add a bunch of static code that's going to allow us to access information from the game outside of our main game library class. So there's a number of things that we put in here. We put our game time, our content manager, our graphics device manager, a sprite batch, a random. You don't necessarily need for graphics. However, it does come in very handy instantiating one random in your game. And then we keep track of some gamepad state. And one of the quick ways to handle this is to go in, and I've named these things by basically an abbreviation. You can choose to do it that way, or you can write out the full name. I'm a big fan of being able to type out everything without having to tab over. I guess it's mostly just personal preference. So gamepad state, T-A-T, oops, S-T-A-T-E, there we go. And we let Visual Studio do the hard lifting. So now we got a whole bunch of properties here so that our things are hidden. And additionally, we've added some code in to pull out, oh, we need an iGame. We've added some code in to allow us to interact with the game and fire certain things off during a normal game. Basically what this is going to do is it gives us the ability to manage game stuff outside of the main game solution. And you're going to see that this is kind of pivotal for being able to get access to things like the graphics device without having to be passing it around all the time. So now we've got all this stuff here. So on create, we've taken the code out of the typical XNA game create method and moved it down here. We've also handled some initialization here and our content loading for stuff that, we need to handle at that point. And then I've got an on begin update and an on end update. Basically, this is just going to help set some of your keyboard stuff. And once you've got this wired into your main game, then you never have to worry about it again. Also, here's a handy little function, keyboard pressed and released, where it will let you know if a button has been pushed down and lifted up, so that you're not writing that code all over the place.
In Section 2, we will learn more about XNA game components and begin to build up our toolset. We'll create a base camera, a variety of game components, including one to manage all of our cameras, and then we'll set up a test scene so that we can see everything in action. So let's go to Larry to see more about the base camera.
We are going to start out by adding what I like to call a noun. A lot of cases this can be also called maybe an entity or a base object, but I find that if you call them nouns, it's a little bit easier to understand what they mean. A noun is something that exists in real three-dimensional space. Also, we are going to add an iNoun interface, just so that we can give us a little bit of flexibility when we pass these things around. So here's our iNoun and the code. Right there. So the iNoun has a transform, a position, a facing direction, a up, forward, and a right. Basically, this is just a bunch of code to help us get ourselves oriented and move things around. The noun is going to have, obviously inherits from iNoun, basically just implements that interface. And everything is driven off of this one matrix transform here. We just pull back all the other stuff off of this matrix. So that's going to tell us the scaling, rotation, translation about what this object is doing. Let's do a quick build. Make sure that everything's working. Okay. Next, we are going to change a few things here. We're going to rename these so that it's a little bit easier to find our way around as we go forward. This will make more sense kind of as we go along. So we're going to name the core library as 00_core. Now we are going to add a new project, and it's a Windows game library, and we're going to call it cameras. Then we're going to go back in and rename it 10_cameras. So now what this is going to do is this is going to set the default namespace to camera without having it be _10_camera. And these numbers here will help keep our libraries in order so that we can visually see where our dependencies are. Then, in camera, we are going to add new enumeration, and we're going to call this eCamera type. This is going to give us the ability to reference our cameras without using reflection. And there we go. And right now we're just going to call it the camera type of none. And I just want to point out, here's a good time, just as good a time as any. I'm using power tools. So if you look at the code on pretty much anything here, this scroll bar here is from Visual Studio Power Tools. And it's just a really handy way to see where you're at in the code. So now we need to add an interface for our camera. And this is just going to be all of the must-have items on cameras. We got a projection of view, position, frustum, and here's our camera type. And then we call update. So now let's add in our base camera class. We're going to call that camera base. And in there, we are going to set it to being an abstract, which is going to ensure that we never... So we're going to set this as an abstract. That way we know that we can never actually create a camera base as an instance. We've got a noun in here as its target. We treat it as a noun, or we inherit from a noun, and then we give it all the interface of iCamera and by default iNoun. So here's all that stuff. And here we pass in a target for it to look at, and then we set its position when we create it, and we send in the type. And on update, because this is an abstract, we can call the base update to set the view times the projection as the frustum. You don't always have to do that, but it's handy to put that code right there. Okay, so let's build this and see if it works. Build succeeded. Okay, and there we go.
Now let's take a look at XNA's built-in game components. In the XNA framework, Microsoft has given us a very useful tool that will lead us to write simple and robust code. This tool is the game component system. But what is a game component? A game component is a modular class that specializes in one task. This task can be anything from displaying a frames per second counter to managing collision detection and more. A game component can handle anything you like in a clean and modular way. Game components are meant to be very easy to write and manage. In fact, XNA handles all the work in the background. There are also two types, a regular game component, which is meant for non-drawing tasks, and a drawable game component, which is meant to draw to the screen. To create a game component, all we need to do is create a child class of the game component class, override the necessary functions, and add it to the component list, and the framework handles the rest. Each component consists of two main functions, initialize and update. Both functions are pretty straightforward. Initialize is where you set up your internal state, and update allows you to change state between each update call. Drawable game components also have a draw function, which draws data to the screen. It may look similar to the game class, and that's intended, as each function under the game component is called in the corresponding function under the game class. That being the case, we can affect when the function of all components are called by placing the base function call in an appropriate area. A good general idea is to either place this call at the beginning or end of the corresponding function call. Just remember, all components are called when the base function is called. Now, there might be times when we want to access a certain game component from another object, such as communication between two components. In order to do this, we can use the game services under the service property. We simply add our component and its type to the collection. From there, we can extract the component we need by calling game.services.getService and pass in the type of the component we want to access. All we have to do is cast a returned object to the type of the component we're looking for, and we're ready to use the component manually. Here's an example. Overall, XNA game components give us a quick, easy, and clean way to structure our code. Once we create them, XNA handles them automatically. We can have components that just update and components that also draw something to the screen. We can also access different components from each other by extracting them as a service. Now let's take a look at the first game component we'll be using, the Camera Manager. Our Camera Manager component will be very straightforward. It will hold a dictionary of all of our cameras and a variable for our current camera. This will enable us to change which camera we're using when necessary. It will also allow us to add new cameras and draw necessary debug information. So now let's take a look at the code. When we first open our solution, you'll notice that we have a new game library called Game Components. If we open this up, we have Camera Manager and Player Component. But please disregard the Player Component, as we'll be covering that in the next video. We also have the appropriate references to Core PC and Camera, which are necessary for the code to run. Let's take a look at Camera Manager. Inside the Camera Manager, you'll notice that we inherit from the drawable game component. This is necessary for us to have the interface that we were talking about before. We also have a current camera type, which is simply an enumeration. Let's take a look. Right now it's defaulted to rotating, but later we'll have more. We also have a dictionary sorted by camera type and the iCamera interface. iCamera interface is simply an interface that we use to unify all of our cameras. Each camera will have a projection matrix, a view matrix, a position, a bounding frustum, a camera type, and also have an update function. Now if we look, we have the same interface that we were talking about earlier. We have an initialize function, an update function, and even a draw function, because this is a drawable game component. In our update function, you'll see that we will actually change the type of camera whenever we hit the tab key or hit the left shoulder button. But right now, it'll stay at a rotating camera the whole time. In the draw function, we also draw some debug information, such as the current camera and the position of the current camera. We also have our public interface for the rest of the code, which is an active camera property, which will return the current camera that we're using, and an add camera function. This will add any additional cameras that we develop in the future. Let's see how this is wired up in our game. Go over to Game 1. You'll see that we have our Camera Manager variable. We instantiate it. We add it to our game components. Notice that we add this before the initialize function call. If we do not do this, the initialize function under Camera Manager will not be called. We go down to Load Content, and we are actually adding our first camera, the rotating camera. Let's take a look. In rotating camera, we have it inheriting from camera base, iCamera, and iHandles input. We have our position set in the constructor. In our update call, we are figuring out the angle based on the total game time seconds. We're calculating the position, and then we're setting the view and projection matrices based on this position. This will basically have the camera rotate around the scene. So let's see how it plays. Go up to Run. And there you have it. Rotating camera. Slightly rotating around the scene, viewing various different shapes. You can see that we also have our debug information, including the camera type and the current position of the camera. In the next video, we will see how to add this scene and how to add the player components.
Next, to build out our scene, we are going to add some kind of dummy code here, just so that we can get some stuff showing up on the screen. And we're going to make a model extension. And what this is going to do is anywhere we have a model, we can call off of the model by dotting off of it, draw, and then it'll recognize the model that we want to draw. That's this model at this. And this is just this is a notation that I personally like to use because it helps you keep in mind that you're using an extension approach. And then we pass in a view matrix, a projection, a position, and a scaling and rotation. Now notice that we're doing this in our core. If we were doing this at something higher than the camera, then we could be pulling those from the camera manager with a minor change of making this static here and that static there. Now, anywhere in the game above this level 20, you have access to the active camera. However, since we're setting this one up at the core, we won't be able to use it. Now we're going to make a quick race to getting some stuff on the screen. So I've put some content already into this folder. Go like that. And I'm including a font here, just because every once in a while it's handy to have a font available. Now, we're not using the default content folder here. We're using the game content high def folder when it gets built. So we need to make a change in our content manager setup, and we're going to do it at the game level. So instead of content root directory, we're going to do it like that. Now we're going to add in some models. And you always add your content in the onload content method. So that's there. And we need a place to store it. So we'll declare that up here. That's just a dictionary that holds the name of the model and the model itself. This is where we want it. So we add in a new player component here. Okay. And our player is a drawable game component. It handles its own input, and it's got a noun in there. But other than that, it doesn't really do very much. So let's get rid of this one, because we do not want him. Okay, that makes things look a lot better. Let's get rid of that. Got a namespace issue here. Let's fix that. This should be Windows Starter Game. Okay. Yeah, it's okay to save that. Let's close this stuff out. Let's add a content reference to the one that we're using. And then let's start her up. Oh, that's right. We need to go back in here. And in our game, on the onload content, on the update. I've got an on update, but I do not have an on begin update, which takes a game time. Now we run that. And there we go. We've got a rotating camera and some models to look at. So that concludes this section.
Hello and welcome back. In Section 3, we'll look at some tools that will make our lives easier during development. We'll look at integrating a frame rate counter, 3D grid, 3D primitives such as boxes and frustums, gimbals, and some other useful concepts into our codebase. But first, we should be aware that most of the tools will be adapted from Microsoft's official sample code. In particular, we will be borrowing code for the frame rate counter from the collision sample, the grid from the vertex lighting sample, and the shape rendering from the shape rendering sample. For more on these samples, please see each of the provided links. Now, onto the tools. The frame rate counter is one of the most useful debugging tools that game developers use today. It shows us an approximate amount of frames that are displaying on screen at any 1 second. This is very useful to us since it's widely used as a measurement for performance and can help us see how new code affects a game. Also note, we want to aim for a range of 30 to 60 frames per second. Anything lower will make our games look slow and choppy. We'll also be using a 3D grid. The 3D grid simply shows us a graphical representation of the X and Z axis. While this might not seem useful, it will prove to be very important as we move our models throughout the scene. It will also allow us to better tweak certain speed and distance values easier. We'll also add some shape rendering to our toolset. This code will use 3D primitives to draw things like collision boxes or camera frustums to the screen so that we can set up our scene a lot quicker and easier. Also note that a lot of this code is very similar to the 3D grid as well as our gimbal, since both use primitives. Lastly, we will be adding a gimbal to our tools. The gimbal is a simple yet important tool. It gives us a graphical representation of the origin of a coordinate space. This, in conjunction with the grid, will allow us to orient our scene with speed and ease. Now we know a little more about the tools and their uses. Next, we'll take a look at the actual code and how to wire them up in our codebase.
First, we will wire up the gimbal, primarily because it is just crazy easy to do. So, to do that, we simply, let's put it right towards the top here. And we need to add a reference. Let's take a look and see what that looks like. And there it is. You can see it inside that box. We got a red, blue, and green line. As also, we got some X, Y, and Z showing in the top right-hand corner to give us an idea of which is which. So we can look at this and say, okay, our shapes are being drawn in the X, Y plane. And they're all drawn at Z equals 0. So gives us a little bit of reference information. Next, we are going to add the debug shape renderer. It's got a little bit more to it. We need to go in here and on the initialize, add that and our reference. And then in the draw, like that in the draw. And I'd like to point out here, so we're using the Microsoft samples in this level 30. And so we can send in the view and projection off the active camera like you normally would, or you can go in and refactor the samples to use our shared library. So the gimbal, I'm using the shared library approach. For this Microsoft sample, I haven't touched it at all. And then we don't have any shapes that we're adding at this time. Let's go in and add a shape. And we'll do that inside load content. So we're going to create a 4x4x4 bounding box. Call it rosy brown and have it draw for 30 seconds. If you put past nothing in it, it'll only draw once. So there you can kind of see it. It's not necessarily the best color, but you can see it highlighting the boxes there. So that's working. So now let's add the frame rate counter, and we'll do that right here. Include that. This one, we're going to make a small change to. We're going to make this use our shared resources. So let's go in there. Counter. And we don't want any of this. And we won't need that. And for these, we want to use the shared resources one. Include that. We don't call that sprite font, we call that debug font. And this is the content manager. So one of the nice things about this is code that we're not really ever going to need to change. So once we've got this working, we should never really have to go back to it. And we need to change the path that this is loading from. Actually, I take that back. We don't even need that, because it's already handled by the underlying framework. So we've added our frame rate counter here and just passed in a new instance. And voila, we are getting a terrible 10 frames per second. We'll come back and look at that here in a second. Let's get a little bit more stuff into our game so we can have a better view of what's going on. So let's wire up that grid now. So we'll make a private grid here. And then, just like they did with the sample, we're going to have to do a little bit additional work. So on the update, we want to set our projection and view to our camera. And then I'm going to need to call draw on it. And last, we have a little bit of extra initialization stuff that we need to do. And we will handle that here in our load content. Oops. Take the graphics device here that is running off of the shared graphics device, just like we did before. Graphics device. Okay. Now everything should be wired up. Fire it up and see if we get a grid. Oh, of course. This should be the shared graphics device. There we go. And let's stop that quick. And just double check that we have removed that one right there. Okay. So you'll see as we do more of this through the game, that it'll actually get easier to remove these and fix them. Or if you find that you're passing things around too frequently, that it might make more sense just to move them into the shared resources. And there we go. There's our green plane. Let's change the... that's good for now. So, what's our next step? Well, if we look at this, we will see that we have terrible frames per second. So, let's analyze that and see what we get.
Lastly, we'll be taking a look at two very useful compiler tools, the preprocessor directives poundif and the conditional attribute. These tools will allow us to write code that automatically changes based on which deployment profile we have selected. We can easily remove wasteful debugging tools and code, or even swap platform-specific code at compile time. They also have the added benefit of being checked at compile time only and reducing our overall executable sizes. This results in a smaller and faster build. Preprocessor directives are used by using the poundif and poundendif commands around a particular piece of code. This wrapped code is then detected at compile time based on whether the given symbol is detected or not. In our case, we will be using debug and release symbols. You can also follow a poundif with a poundelse or poundelif to branch and include a separate piece of code. This is often used when building code for two different platforms, such as PC and Xbox. Also note that preprocessor commands can create unintended changes in state. This can happen if you're not careful while wrapping your specific code. Conditional attributes are very similar to preprocessor commands. They are detected at compile time by the compiler and omit specific code based on the given symbol. They also differ in where they can be placed. Due to their nature, conditional attributes can only be used on classes and functions, basically full chunks of code. They also cannot take parameters and must return void. While this may seem restrictive, it comes with an added benefit: promotes safe state. With a conditional attribute, it is harder to change the state of the game due to it not taking parameters or returning values. This makes it perfect for displaying debug information. Unfortunately, we will only be using preprocessor commands in our code, but please feel free to use them in yours. And that wraps it up for this video. Now we know how to effectively use .NET's compiler tools for our toolset. In the next section, we'll take a deeper look at cameras. Welcome back. In section 4, we'll take a look at creating advanced cameras. We will cover some general background of cameras and how they're used in XNA. We'll then take a look at creating an orthographic, chase, first-person, and third-person camera, and implement each one. So let's get started. In video games, the idea of a camera is just that, an idea. It is more of an abstraction of the real-world thing, meaning it just simulates how cameras behave. In fact, cameras tend to be invisible in the game. They can represent any kind of view you can think of. This can range from a first-person view, commonly seen in shooters like Call of Duty, to overhead views seen in most modern real-time strategy games, and more. But the most important thing to remember is that cameras are made up of pure data, which come in the form of two matrices, the projection matrix and the view matrix. The projection matrix is simply a way to map all of the pixels on the screen to the simulated 3D world. In XNA, we can create this by using the create perspective field of view function and pass in the field of view, the aspect ratio, and the near and far planes. The field of view controls the size of our view frustum and is represented by a certain number of degrees, the most popular being 45. The aspect ratio maps directly to the ratio of our screen. It determines the rough scaling of the scene. Lastly, the near and far planes help XNA determine when to not display items in a scene. Anything closer than the near plane or further than the far plane will be culled or not displayed. The second matrix we need is the view matrix. This essentially handles what the camera views in the scene and is created by calling matrix.createLookAt. With the view matrix, we have three parameters that we can control. The first, position, is simply the location of the camera within 3D space. The next parameter, camera target, determines where the camera is facing. And lastly, the up vector helps determine what the orientation of the camera is. This controls whether we show the scene upside down or any other rotated way.
So to save time, I have the entire camera here. Strategies open. I've created the cameras, and I'm just going to include them and discuss them as we go. So here's our orthographic camera. We've created a camera type, which is orthographic. So here's our other camera types I've commented out for now. And the orthographic camera, the orthographic camera has a little bit of controls here, so you can move it around. And in the camera manager, we have this method here, which gets color, and it just displays the color that we have for the bounding box of that camera. And here in the draw, we have, if we're looking at it from the rotating camera's perspective, it will show us basically a key as to which camera's color is which. To get this finished, all we need to do is add in our camera here, and we're good to go. So here's our rotating camera, and if we tab over, here is our orthographic camera. Note that we're at 333, and if we go back into our rotating camera, you can see that, the large gold box is the viewing frustum for the orthographic camera. And there's the orthographic camera again. Okay. So next, we're going to look at getting a camera that's going to chase the player. So next, we're going to do a chase camera. So the chase camera is basically just going to follow the player around. We've got it set up to run on a spring. When the player moves around, the camera will just kind of drag behind the player. Okay, we go back in to our camera manager. And uncomment the chase stuff. do that one. And now, as we get in, there is our chase camera. So as we move our snowman around, the camera will try to stay behind it. But you'll notice we're kind of looking down. One of the problems with the chase camera is you can't necessarily control it. So if the player decides to move back underneath the camera is going to keep looking at the player. And it applies to certain types of games, spaceship games, maybe running games. So you got to be sure to choose the camera that you want for the right application. So let's look at that camera just a little bit closer here. So in the chase camera, we declare adapt oscillator, and here I'm calling it mobility. Give it the target, which is, in this case, base of the snowman. We tell it which noun is going to be moving, which is the camera. The camera acts as the mobile part, and then we give it an optimum distance. So next, we want to look at setting up a first-person camera so that we'll have the ability to look around. The first-person camera got a lot more to it. So let's include this. Let's start looking over the code here while we finish plugging it in. So, first-person camera, what it's going to do is it is going to use the head of the snowman as its reference point. And when it does that, it'll allow us to look around and kind of get a better feel for what's happening in our scene. So not only can we navigate, but we can move the camera up and down, etc. So here, I'm passing in this vector 3 forward, which is, it's going to get overwritten on our first cycle, but we got to pass in something that's not null there. So let's take a look and see what it looks like first. Then we'll come back and kind of, so we'll do a quick overview here of where we've gotten. You'll notice that the chase camera starts out kind of a long ways away from the player. And as we look through the orthographic, we see that the small, the near plane of the chase camera. And then the chase camera kind of snaps into position. And then we have our first-person camera. So if we go back through, you'll see that now our first-person camera has been initialized. And you can see the chase camera behind the player and the first-person camera in front of the player, and the orthographic kind of coming in from the top right hand behind the player. So if we go back in and look at our first person, we can now look around and we can move, and we can also look up and down. One thing that I didn't implement here is snapping. In a lot of games, if you look up and walk forward, the camera will snap back down. Tokens, snowman. If the head moves, and here we can use a whole plethora of different ways to move the head, the net result is that the head moves left and right with the body. There may be instances when you want to treat the head differently than the body. However, those are kind of one-off situations, and you're going to have to redo this code anyways, because for, say, human figures, what you're actually going to be attaching to is the bones and not necessarily a noun. And last but not least, the third-person camera. Well, let's say last but mostly least, third-person camera really, really trivial camera. It's going to have, let's finish wiring this up quick. It's basically going to be a static camera that follows the player around wherever they go. Nothing too fancy. In fact, it's mostly just a copy from the chase camera, taking out all of the complicated stuff, and is really just more of a baseline chase camera than anything. Go into game here and give it a place to start from. There we go. So we create our third-person camera, we target it at the player, and then I'm passing in this 3 here as a float. And that's just a distance. So that is the look from offset for that camera. So it's going to be 0, 3, minus 3 from the target. And that's really all there is. There's no control here. It's all laid off on the player. So if we go in here, and I'm going to tab through all of these just so that we can get all of our cameras in perspective and go back to our rotating camera. The orange camera here that is now closest to the screen is our third-person camera. So when we get back in there, oops, third person. So now we see that if we go forward, we're looking at the face of the player, and this is if we go backwards. So it's kind of just the opposite of what you get with the chase camera if you pass it in with the distance like this. However, you can set it up pretty much however you want. Just in most cases, a true third-person camera isn't actually controlled by the player. So there you go. We've got a whole bunch of cameras now, and we have a player component. And let's just give a quick look around here. So lots of cool stuff to look at. And we will come back in the next section and get a little bit closer to having a full scene. In section 5, we're going to start understanding more about models. To do this, we're going to need to look at simplifying our models, getting some drawing order added. We're going to learn how to work with multiple model types. Then we're going to build a model at runtime, and then we're going to look into instancing models. So starting out, we've got a number of models already on the screen. However, if we go in and look at how we are getting them into the game, and we're going to ignore the player model for now, we'll see here that we're taking our models and we're adding them to a local dictionary and then just loading the content. And when it comes time to drawing them, we are here giving them a position to draw and then drawing them at that position. This works really good for simple tutorials and demo code. However, when we want to get a little bit deeper into what is available on those models, we're going to need to do a little bit more. Okay, so I've gone in and added a collection of simple models, and what this has is it has our model, our bones. It's got this array of instances. Note this isn't an instanced model, it's just a model that has a number of instances. Then you can load it by sending in a path and a number of transforms, and you can add instances. I don't have anything for removing instances because these are kind of assumed to be like trees and fences and things like that. Then we got a draw here, and we've got this structure that we call our model info, and that's got the world matrix, which is a rotation, scaling, translation matrix, and the local bounds of this model, as well as this helper class, which basically ensures that when you build the bounding box that you have your translation inside it. So we're going to add that into the main game code and gut some of the stuff that we have in there right now. So I'll start out here just to show you what we need to mess with. Switch that to a lowercase m, and you see we've got some errors here in loading content, and then another error down here in draw. Well, first off, we don't want to be instantiating new positions for these things each time. So instead of doing it down here, we're going to force the draw. Get rid of that stubbed out. We're going to force the draw into the simple model. And we need to go up here and change this to simple model. One thing you need to be careful of here, and I've run into it a number of times, is that the draw method on a model will give you some different results other than your native draw. So if you were to call this particular draw on the model with a world view and projection matrices, it'll actually fire off of the base XNA draw method, which is something that you do not want. Then in the load method, we're going to take this and add a whole bunch of code. Some of this came from down at the bottom where we were making the instance each time. But I'm using tuple here, which is just kind of a convenient dummy structure, I guess, so that you can make a small structure, use it once, and then throw it away. So this is just code to get all of my locations into a variable using that same iterator. Then I add to my dictionary my simple models. And the process of doing this, I tweaked some of the size. But then what you get is you get all of your models separated out like that. And notice that we didn't really take a hit in our frames per second. If anything, it might be just slightly better. And there we go. Our next step, if you go in here and watch that, what you're going to see is that every once in a while, the models, let's see if we can get to a camera where this will be a little bit easier to find. There it is. Get to the end here and look around. So right here, you'll note that those balls are supposed to be, or those spheres are supposed to be drawn in the back. However, they're being drawn currently in front of those cylinders. So if I go back over here and look, those spheres should be in the back. However, when you look at it, they are getting drawn in front of other things that they're supposed to be drawn behind of. So we've got a drawing order problem. So let's go in and make a small manager to handle drawing order.
In this video, we will be taking a look at our Draw Order Manager, but first a word on some of the theory behind it. We will be using the painter's algorithm to help us determine how to draw objects to the screen. The painter's algorithm is essentially the simplest method for rendering objects. In fact, this method has been around for thousands of years. The reason it is called the painter's algorithm is due to how you draw things. Normally, a painter would paint a foundation or background layer first, then paint each layer on top of that. The algorithm does just that. It displays the furthest object in the scene first, then renders each closer object until the closest object has been drawn. For our Draw Order Manager, we will be using this technique exclusively, since it is the easiest to implement. The Draw Order Manager will contain a collection of drawable objects, but not necessarily all of them. We'll be able to add and remove objects just like any other collection. We'll then sort objects per update call based on the proximity of the object to the current camera. And this way we'll see our scene come alive with overlapping objects and a different perspective. So now that we've talked theory, let's look at the code. To start off, open Game Components and Draw Order Manager. This class is a self-contained drawable game component which means it will update itself and draw objects to the screen. First, we have a helper struct, which will help us gather the necessary information about each entry for our draw order. This will help keep our code and algorithms clean and easy to understand. Next, we have our dictionaries or maps of our drawable objects. Here we store the actual data directly related to the object we want to draw, whether it be a texture or model info. We then have two different functions to add our objects to our manager. Notice that the second one gives us the ability to input starting transforms for our objects as a kind of shortcut. Since our manager is a game component, we have the necessary functions, even if they're empty. But the most important one is the update function. In this function, we establish an initial draw order among elements, and then sort the drawing order based on the distance to the current camera. This is where the majority of the work will be done and what will take the most time, since all of this is done per update call. Lastly, we use our corrected drawing order to draw each of the components to the screen. And that's it. Let's run the code. Now that we have the code running, we can see how objects closer to the revolving camera are drawn first. This is especially noticeable when we look at the mesh black boxes as they pass closely to the camera. Also note that we have a slight bug in our code that isn't sorting the cylinders, pyramids, and cubes correctly. But worry not, we'll fix that in future videos. And that's it for the Draw Order Manager. Next, we'll look at models.
The next thing we need to talk about is new models. I've added this folder for instance models. One of the things that you need to keep in mind on these models is that not all models are made the same. So here I've taken this cone FBX, I've copied it, and I've made some quite substantial changes. Now it's not exactly easy to see just by looking at it here. However, if you look at it in Diffuse, which is a merge tool that I enjoy using, you'll see that there's actually a bunch of differences. At the bottom here, I've added in a texture for the instance model. So even though both of these models are exactly the same on the surface, underneath there's some fairly substantial differences. You can see every place here that stuff doesn't line up. And then another thing to keep in mind is that if you look at the properties on this thing, you'll see you have an asset name, a build action, a content importer, a content processor, copy to output directory, a file name, and file path. However, that's not actually all that's available there. So if we unload this and then we go in and edit it, one of the things that you can do is you can add in a statement that tells the compiler to make tangent frames. Basically, this will just make normals. However, you can only do this on models that have a texture assigned to them. So the models that we have been using don't have a texture in the model code. So if you try, our build succeeded. But let's get rid of that game. But if we go in here now instead, unload the project again, edit it, and try to add tangent frames to something that doesn't have a texture in it, and we run it, it will give us an error saying that we don't have a texture coordinate. So even though the models themselves are pretty much the same, the files that we're loading them from are substantially different. And that's one of the things that you need to keep in mind. You also need to keep in mind that XNA does some optimization of your models at load time. So building models in-game isn't going to be quite as efficient as having a static model that you can compile at the beginning of your game. Why don't we go in and start building out this instance model, because there's a bunch of code for it. So for the instance models, we are going to do hardware instancing, slightly different than some of the other forms of instancing that we've done so far. What this is going to do is it's going to push the information that we need to the hardware and let the hardware deal with all of the heavy lifting. One of the other things that we're going to need here is we're going to need a drawing helper, okay? And so we've got a special vertex declaration here. Now you can take these and add them inside your graphic structures here separately, like I've got here. So what this is going to do is, it's actually quite complicated, but it's going to take the model and it's going to push it off to the graphics device, and then it's going to push all of the instances in it to draw at one time. There it is. It's going to push the entire list of matrices for transforms into the instance vertex buffer and push all of them at once to be drawn. So it's a massive speed up in time. We are going to need to add something to handle this, however. We're going to need to add some pipelines. So let's add a new folder here and call it pipelines. Then inside there, we are going to add a new solution, which I've already made. Work in progress pipelines, instance model pipeline. And then we need to build this thing quick. And that succeeded. Now we go in here to our instance model, add in a matrix list. Then we'll add in our instance location. Need to uncomment that one. And then we need to handle support in our draw order manager. Add in a dictionary for those instance models. Add in support inside each case statement. There we go. Be sure to update them like so. And then we need to draw them. And that should be good. So our instance models are not very impressive here. There they are, just a couple hundred or so cones stacked up, kind of going off into infinity. But you'll notice that they don't really affect our frames per second rate. Right now, we're kind of treating them as one big model because they're all going to draw as one model. So if one of them's on the screen, they're all going to attempt to draw, but you don't take a very big hit for it. So now let's move on to adding in some cubes.
Lastly, we'll take a look at primitives. But what are primitives? They are the simplest 3D graphical unit that is drawn to the screen. You could also think of them as the building blocks of our scene. Primitives consist of three-dimensional vertices that combine to make things like lines, dots, triangles, quadrilaterals, and polygons in general. But XNA only uses certain types of primitives. Currently, it supports creation of lines and triangles in either a list or strip collection. However, there's a slight difference between a list and strip. In fact, strips were made to be more efficient than lists because they require less data and infer more information based on the data passed into them. In this way, line and triangle strips should be used more than their list counterparts, as a result in faster code. That being said, using a list is applicable in special cases, like if we had a primitive of relatively few vertices. Which leads us to why people generally use primitives. As the basic units of the 3D scene, primitives make up all character models and scenery, but in XNA they're more involved with procedurally generated content. This content consists mostly of skyboxes and terrains, but can be anything else needed at runtime. Primitives are also extremely useful for debugging purposes, such as showing collision boxes, camera views, and model skeletons, as we've already seen. Lastly, there may be game-specific instances that require more explicit use of 3D primitives rather than models. So now that we know a little bit more about primitives, let's take a look at our code. In this example, our primitives code will be a bit simple, but a step towards something much larger. First, open core and graphic structures. We see that we have a few new files, the most notable being these three. So first, let's take a look at the cube code. Inside of the cube code, we have a vertex buffer, an index buffer, a basic effect, and some model info. We'll look at the basic effect in a later section. The vertex and index buffers are simple buffers used to communicate with the GPU, which handles the vertices and indices that we later define. Scrolling down, we see the creation of the actual vertices and indices for the cubes using a vertex position texture array. This is where the actual 3D points are determined and translated according to our model info. It also stores texture information if we want to load a texture onto our primitive. Further down, we have our actual draw call, which takes the configured vertex and index buffer. Also notice we're using a triangle list for this instance instead of a strip. Now let's look at our factory, where we'll be creating our cubes. In this class, we have 3 standard function calls to create one of 3 different kinds of cubes: a default, a metallic, and a psychedelic. These 3 types of cubes are also reflected in our cube type enum in this file. Each of these factory functions call a generalized function, make, that can handle each call internally or externally. Lastly, we want to add these cubes to our scene, so we go to game1.cs and down to load content. We've commented out the other models to easily see our cubes. To add cubes, it's as simple as calling the add function on the draw order manager, and that's it. So let's see it in action. Now we can see we have 3 different cubes on there. We have a default green cube, metallic, and a psychedelic cube. Also notice as we flip through the cameras, each of the camera views are also shown using primitives. Well, that's all for this section. In the next section, we'll talk a little bit more about shaders. Welcome back. In section 6, we will be covering shaders in general and how to implement them in XNA using HLSL. We'll look at a quick introduction at what shaders and HLSL are, as well as creating a simple shader effect. We'll also see how shaders work by looking inside of them as we create our first one. Lastly, we'll create code to manage all of our shaders and explore some alternative methods to using them. So let's get started. The first thing to understand is what a shader really is. A shader is simply a program that runs on a GPU to manipulate the appearance of the game. It's used to change the position, shape, and color of the 3D objects in our scene. But shaders are best known for simulating a variety of different lighting effects, essentially shading the world based on what lights we do or don't want, hence the name. Shaders are mostly used to make games much more visually appealing, and they can do this in 2 different ways: a photorealistic way and a non-photorealistic way. Shaders are responsible for much of the realistic water, light reflection, and shadows seen in most games. Without them, most games wouldn't look half as nice as they do today. Some games even use them to create non-photorealistic scenes, such as cell shading and other non-realistic views. Besides making our game look good, shaders also allow us to offload some computation to our GPU, since it can handle some calculations much faster than our CPU. Here are some examples of some non-photorealistic shaders, courtesy of Microsoft. In XNA, shaders are created using HLSL, Microsoft's proprietary high-level shading language. HLSL was specifically made to allow the creation of shaders in DirectX applications. It features a C-based syntax as well as access to many 3D math functions. Shaders in HLSL come in 3 distinct flavors: vertex, pixel, and geometry. Vertex shaders are run on any vertices passed to the GPU and are mostly used to transform these vertices in 3-dimensional space. They can also help with texturing models by generating texture coordinates. Pixel shaders, on the other hand, run on each pixel within the vertices passed to the GPU. Each pixel's color and transparency can be altered, but is usually done through a number of different lighting calculations. Lastly, geometry shaders can be used to generate more detailed models through tessellation and also run on vertices passed into them. Unfortunately, geometry shaders are a bit advanced, so we'll be skipping it in this section. Lastly, here's a look at how XNA processes shaders. We can see how it starts with our raw vertex primitive and texture data, moves through each shader, and displays to the screen. And it's as simple as that. Now we know what shaders are and how they're used in XNA. In the next video, we'll go about creating our first simple shader. In this video, we'll be stepping away from our main body of code to focus on our first effect. To create it, we must first create an FX file. We do that by going to Content, right-clicking, and adding a new item, and selecting Effect File. This will create our effect file. Also note that it should be kept in our content project, as it will be loaded the same way that our other content is loaded. Now let's take a look inside. The first thing that we'll see are three 4x4 float variables, world, view, and projection. These are the parameters being passed in from our C# code, and each represent a matrix with 4 rows and 4 columns. Also note that these matrices will be our camera matrices, which are essential for our shader to properly work. Next, we have two structures, vertex shader input and vertex shader output. These structs help us combine all the necessary data for our vertex and pixel shaders. As the name suggests, they're written to be either inputted into the vertex shader or returned from the vertex shader. Also note that the output of the vertex shader is also the input of the pixel shader, so we could easily name this second struct pixel shader input. Further down, we have our actual vertex shader that will do the necessary work we need. By default, it simply uses some math functions to properly transform the vertices from world view to screen view. We'll leave this as is and focus on the pixel shader. Next is a pixel shader. This is where all the lighting and coloring happens. Here we can do any number of lighting calculations to either make our scene realistic or non-realistic. Right now, it simply returns a color red for each pixel, which will render the polygon passed to it in red. We'll see exactly how that looks in a minute. One important thing to note is the capitalized keywords after each shader function. These are called semantics. Semantics tell the corresponding shader compiler how to properly map the input and output to each shader. Without them, the shader would fail to compile or run, since it's missing essential data. Lastly, we set the state of our graphics device with our technique block. An effect can also have multiple techniques for different effects, but in this instance, we're only using one. We can also have multiple passes, which are usually used by complex effects to stack multiple shaders on top of each other. Again, we're sticking to a simple example, so we'll have just one pass. Finally, we can see that we have two states, one for each shader function. These are essential for our effect to work correctly and can be compiled by one of several different vertex or pixel shader compilers. Now let's take a look at the C# code. In our C# code, you can see that we have a model and an effect object. Each of these are loaded in the load content function. Down in the draw function, we must first set the current technique we want to use in our shader. So we have it at technique 1. We then loop through each mesh in the model, as seen before. We also loop through each model mesh part and set its effect to our custom effect. After setting each parameter in our shader, we can finally run the program. And there we have it, a red ship. Not too impressive, but let's see how we can change it. Going back to the pixel shader, we can tweak the color value, setting it to blue, and run it. Now we have a completely blue model. But what if we want to see its texture? That requires a little more code. First, we must create a parameter to store the model texture in our effect. We then have to create a texture sampler, which essentially creates a configuration for the graphics card to understand how to handle the texture. After adding the needed variables to our structures, we can then generate our color by calling text2d, which maps the sampler to the texture coordinates generated by our vertex shader. From here, we can return the color, or we can manipulate it to create interesting effects. So there you have it, our very first effect. In the next video, we'll talk about how to better manage our effects.
To make the shader management stuff, we're going to go into our core and add another folder here, and inside there we're going to have an interface called an eye shader. Really simple. All it has in it is an effect. We are going to create a override for the effect so that we can do some management as we pull it in. We'll talk about that here in a second. We're going to have shader input enumerations that we can use, and our shader library is going to be a simple dictionary. We're going to add a folder called IO that has string extensions, and what this is going to allow us to do is it's going to allow us to pull back the file name from a path. We also have this simple effect that I have made. This is a chicken of the woods. It's a fungus that grows native in Minnesota. And what we're going to do with this effect is under the texture section, we have given it a relative path. We've uploaded its image size. So we set its image to 128 by 128. And then we have this format of 32-bit color. Now, how this is used is when we read in our shaders, we can pull in our shader into an effect, but without keeping track of which shader has which parameters, it's going to get very, very difficult. So as a developer, you set up a paradigm where your attributes inside your effect, here I've given this normal texture a file name attribute, and you can give it one or you can give it many here. And when we read in the shaders, we go through the annotations there and then pull out that information. Basically, in the effect file, as long as you have everything structurally supported, that effect file can keep all of the information about what it needs, what stuff is passing into it, and what you're going to do with it. Quickly go in here and show you that it is getting called up in the game. So we'll go in here. We're not going to need any of this stuff. So let's get rid of that. Comment that out for now. And put in our shader there. We need to include that. Then we're going to go down here to the draw method. And at the end, we're just going to draw that texture out. So we also have this texture library, and that's just a dictionary of textures. And when we load it in, we can reference it in there. Now let's fire that up. And you'll notice in the bottom right-hand corner here, you see that chicken of the woods that we're drawing, just to prove that we actually pulled it in and that it's in our texture library. So now we're going to add in some slightly more complicated models using shaders. I've acquired a model from David Murphy that is a simple model. It's just a cutting board, and he's given it to me in two forms. The normal cutting board form is binary encoded, and the cutting board 2 form is ASCII encoded. Also, each of these comes with a diffuse and a bump / specular map, and I've copied in the chicken of the woods as what I'm calling the cutting board crazy spec. So we're going to start out here by getting some support for those things. So we go into our game components, and we are going to need in core. We are going to need a new model. We'll include that. And what this model is going to do is it's just a simple model, and it has a known shader, which is this normal diffuse shader. We instantiate that statically, since we know that this is going to always be built with our solution. We include the shader for it as part of the solution. Then our model loads the shader textures into the library so that they can be reused in other places. Then we have our normal diffuse model here. Let's just fix that quick. That should do the trick. There we go. To handle drawing with a shader, we are going to need a new extension method. And so we'll put that into our model extensions. This is basically the same shader that we used up here. However, we've hard-coded in the parameters so that we also have a light position. Then we need to go into our draw order manager and update everything, because now we were putting in a new model type. Here's our draw order manager, and we're adding in a new model type. Then under add, we want to make sure that we don't accidentally load this one, because if we load using this add approach, it won't hit the custom method that we need. And then we'll put in some support on the next add as well. Then we're going to add in two methods that are specific to adding this normal diffuse model. Those will just add in the new models. Then on our sorting, we need to make sure that we include those models for the sort. And we need to make sure that we include those models for the draw. And then we got a little bit of debugging code down here. We want to make sure that we get the bounding custom for those models. So now we'll go into our game. So now we go into the game method, or our game class, and add in that stuff. And in the draw method, we add in a reference to the cutting board. And then we just need to go in here. Because we're going to be using normals, we need to add in the reference to build the content the right way. So we edit this one, go in here, and in the cutting board FBX sections, we add in our tangent, or generate tangent frames, and save that. Reload this, double check to make sure that we got all the right stuff. We don't want the object. Then we also need to make sure that we have the right shaders included here. So let's update that. And this is the normal spec diffuse shader that is available on the Microsoft website. Here's where shaders gets funky. In our model extensions right now, what we have is the world view and projection parameters. They're pretty much available on every shader. This one we're sending in a light position. However, you might have a different shader that sends in different texture each time, or you want the light to be moving or changing colors, so maybe you have one here for light color. And the way that you're going to keep track of that in your shader is through your annotations and through shader input values. So you'll have to wire each of those up specifically for your case. However, using the approach that I've outlined here, you have some flexibility in that you can make a class, and this just inherits from simple model, that has a knowledge of how it's going to be shaded, or you can refactor all of your existing classes to draw using a shader that you've pulled in. One of the problems with this, however, is that no matter what you do, you're always going to have a little bit of wiring up in each scene. So there's a architectural choice that every developer must make as far as whether to support a specific model type that implements the shader, or to implement a shader so that all model types can use it inside your game. And that's a decision that you have to make on your own. For our next section, we are going to implement a little scene and get something that looks like it would be worthy of being in a video game. And we're going to use this normal spec texture model class. And all of our models are going to be imported using that. That way we can swap out what we want on those models. In section 7, we're going to set up your first scene. To do that, we are going to need to incorporate the Microsoft particle sample. Then we're going to set up the scene. That includes adding some models. Then we're going to introduce the concept of lighting and put that into our scene. Then we are going to create a scene file and load it at runtime. And finally, we're going to go in and debug the metadata, move some stuff around in our scene, just give you an idea of how that works. Diving into the code, we'll see that there's going to be some content, so we'll add that. And in the game components, we'll add Microsoft stuff. So I made this as a folder. I've put the particle systems into a separate folder underneath this. I've created a class called particle master. This takes all of the initialization that was in the sample in the sample game.cs and moves it into a separate class. Then I have this inherit from drawable game component. And then I have added 2 particle systems here. I've added one that I call a fire pit particle system, and another one that I found by accident while I was trying to make a ball of fire that is called a fire pillar. This one is included, however, we're not going to be using it. I'm going to be focusing on the fireball. I've also added the appropriate code in here to support a fire pit for the particle state, and created a method called update fire pit, which goes through and produces, instead of a random point on a circle, it produces a random point in a circle. Go into our game here, fire this up quick just so I can show you what we've got currently. So right now, I've gone through and I've cleaned out a bunch of the stuff that we had been using in the previous tutorials because we want to have a clean slate here. So that all that we have at this point is just the cameras rotating around the origin. Okay, so let's go in here and add the game stuff. So we go into our game and add the particle stuff. We need to include that. So we add our particle component. So then we also need to initialize our particle master particle component, and we'll have a nice ball of fire there. So let's get a little ways away from here so we can take a look at it. There we go. And there's just a burning ball of fire. So the particle sample, pretty straightforward. Let's go back in here so I can show you this. You'll see in the fire pit particle system that we've changed a bunch of the settings from the normal fire, and we've changed the size of some of these things. Okay, so let's move on to adding in some models to make this look more interesting. Okay, so the first thing we're going to do is David has provided us with some more content, and we are going to go in and include that in our solution. So we are going to take under the boxes, first 4 there, we'll take all of the common, we'll exclude the light fixture, the last 2 in the stairs, and here from the table, and then from the bunker, 3 here, and the last 2 here. So now that we have those added to our solution, we need to go in here and edit the content. So we're going to search on FBX. And for each of these models that we just added, we are going to generate tangent frames. Walls, stairs, tabletop, wood leg. Okay. I'll reload that. We want to get rid of these 3 cameras. So we'll just comment them out. However, because of the way that we're operating our camera manager, we do need to go in there and make some changes. Since we know that this is a first-person or third-person shooter game, we know that we're not going to need a rotating orthographic or chase camera. So what we need to do in that instance is hide all of this other code. So you could do that using preprocessor directives and setting up a bunch of systems for making different types of games. However, for all intents and purposes here, we're just going to be living in the first and third person world. So we don't want any of that. And it's best to get it out of your executable because it takes up space. And if you plan on going to Windows Live, you need all the space that you can get. So we have to change here to first person. And then just a little bit more clean up here. We add our references for loading the content in here. And one final modification, we're going to go into our shared resources class and add a background color so that we can change that during the game. And here we go. So our player, 2 cameras, then we've got our bunker floor, and we've got a big wooden box, we have a wall, we have some stairs, we have a small box, we have a tabletop, and we have 4 table legs. So you will find that when you try to place this in game, you'll find that it gets kind of difficult to move these things around. So when you try to move these around inside the game while you're setting up the scene, you're going to notice that it's going to be tricky to get them to move around right. So one of the shortcuts you can take is you can add in modification vectors to help you organize things. And in the stuff that David gave us, he has included a position suggestion, and I've taken that and I've played with it just a little bit, up and down mostly, to get it to work right. So let's go into the game and see what that looks like. So there we go. We've got our fire, and things do not look right. So there's the model. You'll notice that when you get outside of the model, you can see through it. That's because the mesh is one directional. The normals only go to the inside. Okay, and we're still sitting at the 0 plane. So we've got to go in and tweak some stuff here. But we'll take care of that in our upcoming sections. One thing we do want to add in right now, however, is a better use for this fire. Let's make it flicker so that we can get a little bit of light off of it. In order to do lights, we are going to need to add in our core, an iLight interface. And this thing is pretty simple. It's got a light source position and then 3 things here that are not wired up. And note that this is the same thing that is defined in our normal diffuse shader. So if we go into this effect, you'll see that these are defined here. And so we're just going to wire up to the light position and leave the other ones alone. If you want to wire those up on your own, feel free. It'll be pretty straightforward after this tutorial. The next thing that we're going to need is in our game components, we will need to add a flickering fire and also a light manager. So for our flickering fire, we've declared it as a noun. It's an iLight. It's a two-body system, and it's iUpdatable. Pretty straightforward, just some really simple stuff here to move it around, or move around the light source inside of a sphere. If it gets outside of that sphere, it just resets. And in our light manager is basically just a list of light sources, and then for each light source we update it. So now that we have a light, we need to attach it to something. And in our game, that is going to be the fire pit. So here's our pit information as we declare it. Now we need to add in a lighting component. So to do that, we're going to add a light manager, light source of a flickering fire, and we're going to attach that to the pit particles to use as a noun reference. Now that the lighting manager is keeping track of where the lights are coming from, we need to go in and modify how we're drawing the models to leverage that. So before we had this simple draw method. Now what we're going to do is we are going to break it up into 3 methods. And in these 3 methods, we're going to have one that handles a light and one that assumes that there is not a light, and then a base drawing method. So what happens here is you can either call the draw with a light, or you can call the draw without a light, and this will just use a default light color, and both of those will then pass in to the core. If you wanted to extend your light to change the position, color, and ambient color, here would be where you want to do that. So this is our light source position. So we run that quick, and everything's working. However, you can see that there are some shadows here on these boxes for us to use as reference. But we've definitely got some kind of a draw order problem here. So why don't we go in and fix the drawing order issue and come back to the lights then. So the draw order manager that we had was kind of designed to work in the open or outside of rooms. So to fix that, we are going to create an artificial draw order suggestion, because we know that the walls should always be drawn before pretty much anything else. So we'll add a draw order item here, and we'll take that out of our draw order manager. So here's our old draw order item, here's our new one, and in here we are going to just overwrite this whole class because there's a bunch of changes. And what we're going to do then is add in a drawing order suggestion on each of these things. So we need to change the model here, and we're going to go drill down to simple model base. And in here, we are going to add a nullable int as a suggested draw order. And then we're just going to use that as a hint to our draw order manager. And then we'll just use the drop through creation mechanism there. So just add our draw order suggestion in here and then call the base so we can get that. Otherwise it'll just stay null. And we go back to our draw order manager. Let's see if we still have anything else that needs to be fixed. Nope. Try to build it. Our build succeeded. Now we need to go back in to our content here, and then we're going to add back in all of the suggestions. And there's going to be a couple here that are going to be tricky, and we'll address those in a special section. So some of this is going to be trial and error. Now, let's see what this looks like. There we go. Now you can see that the fire is flickering. We got some shadows moving around. We got the table being drawn in front. All the table legs are being drawn where they should be. The table's inside the room. Both the boxes are inside the room. We do have an issue here where the background color is not being sucked up as content. To fix the background problem, we were wiring up the background color. We missed to wire it into the graphics device.clear. That will take care of that. Now, why don't we move on to getting our scene to save and load. So now what we want to do is we want to save. So we've gone through all the trouble of putting all this information in here. But what we need to do is we need to get that into the format of XML. So in order to do that, what we're going to do is we're going to add this thing called a scene definition. And in the scene definition, we have basically one class that feeds into one of each of the things that we load into the game. So if you look at this model, for example, it's got a name, an asset path, a normal path, a color path. It has a list of instances and a drawing order suggestion. All we do is we pass in those things into the class and it sets itself up. And we're doing this in the exact same order that we've defined it down here for our add normal diffuse model. So what this does is it gives us the ability to take the code that we have here and convert it rather straightforwardly into something that we can use for loading and saving. So we will define a new scene definition up here. Then in here, we will convert all of this information so that it's feeding into the scene definition. So all this stuff is pretty much in the same place, just feeding into the scene definition. Then we need to have a way to pull it back out of the scene definition. And we'll add that in right here. Then we can give this a try. Okay, it compiles fine. Now what we need to do is add in the method for saving. So then we add in the save method. We're just going to add it in right there. Then we need to have a way to save the file. So we are going to go into the update method and use our keyboard S to save it. Now you're going to notice that there's some things here that aren't included. To fix that, we are going to go in here and change this from a client to a full. And then add some extra XNA references, and we'll search by component name. And then we'll take all of the XNA ones. This is a little bit of overkill, but they'll get stripped away once we go back to the client references. And this is just so that we can get some of this content pipeline stuff. And this is a bit of a hack so that we don't have to sit down and actually write out the XML. Now we go back in here and add the using, and then we should be ready to go. So when I click the S button, you're going to see a little hang here. There's the hang. That means the file saved. Now we can dig down here. Let me refresh this here. PCX86, and there's our scene file. Let's take a quick look at it. Yep, it's XML, and we'll come back and talk about what that means in a minute. But we're going to cut that and paste that up in our content here, and then we include it. Then we go back up to our load content method, and we can comment out all of this stuff. We comment it out just so that we have it around in case we make a mistake. And there is our scene information. Before we can actually use that, the content is actually going to need our reference to where that thing is declared, where the scene definition is declared. That's in our game components. So now that we've added that reference to the content project, we can build it and then just use the normal content loader. And there you go. Okay, now let's see what kind of things we can do now that we have this content loading. First thing we're going to do is go through and delete all of this because we don't need it anymore. And now we're ready to start tweaking our in-game content. So inside the game, we go in and we can see that the stairs here, we've got a problem. If you get right on them, they look like they're being drawn in the right place. However, if you get a little bit away from them, you can see them through the wall. Well, that's not good. So why don't we go and see how we can fix that. First thing we're going to do is we're going to open up the scene XML file and find our stairs. There's our walls. And let's just switch the order on these things. So this is being drawn 0, this is being drawn 1, and see what happens then. So now, can't see our stairs here, but we get to there, and now the stairs look like they're a mile away. So that's not good. Well, how do we fix this? Well, David has been good enough to offer us another model, and we're just going to include that right here. And we're just going to override this wall, turn that into a wall stairs. Right there. Then we won't need this stairs, so we'll just comment that out. And because we're adding a new model here, we need to once again unload the project. Then we need to go in and add for our tangent frames on wall stairs. And we can save that and fire it up. Now we go over here. Those stairs are, since they're attached to the wall, we don't have any drawing order problems. However, I had been playing a game where I just copy the wall up a couple of times, and we see now that that is causing problems. So we can go back in here and edit our scene once again. This time, take that wall, and we'll change the key name because we're modifying it differently here. Make sure we get the right name. It's here, bunker, wall, walls, war room. And make sure my capitalization is correct. Okay. Now we want just the first instance here, and that's going to be to right there. so we can get rid of other instances. And we want to get rid of the first instance here. 6, 1, 2. Okay. Now when we go back in, we have our stairs being drawn in the right place, but you'll see that some of those other walls are overlapping improperly. I don't like that. So why don't we do this? Go in here, we'll get rid of these walls, comment them out, just go back in and look at it with just one wall. And a lot of times you're going to have to play this kind of a game where you just have to play with the assets until you get what you think is going to look right. So here is what we have right now. You'll note that those shadows look really good against that stairs. Anyways, the way to fix this ultimately is probably going to be to get a ceiling attached to your walls and your stairs, because in the game you're probably going to put in some kind of a portal here, or this is going to attach to another level. And so getting all of that attached as one model might be a good idea. And if you want to, say, move this fire because it looks like it's just a little bit out of the pit, then what you do is you stand right where you think that the fire should be, and you'll notice that we can use that player position to modify the position of our fire. Other than that, we're pretty much good to go here. And yep, that's about it. So let's look at how we're going to put this and deploy it on an Xbox. I'll leave that in there. And yep, time to deploy it to an Xbox.